Alright, so this is a recap of what we learned for lesson 5.6, partial pressures and ideal gas stoichiometry. Before we get into the partial pressures and before we get into the ideal gas stoichiometry, we need to know a little bit more about gases. You need to know what kinetic molecular theory states. And kinetic molecular theory basically states that gas particles move in random motion. They don't stop. They're constantly moving. You need to know that the volume of these gas particles are so small that we could ignore the the volume of the particles. You should also know that we're assuming in this theory that particles are not attracting as much and they're not repelling as much because they're constantly in motion. For collisions are elastic, meaning that no energy is lost. So when one particle bounces onto another particle, none of the energy is transferable. 5. The very, very important concept, the average kinetic energy. Kinetic energy is the energy due to movement. The average kinetic energy of particles, of all the particles, will be equivalent to the temperature of that gas. So all the individual particles might have different kinetic energies, but when you take the average is equivalent, or in this case directly proportional, to the temperature. And it's in Kelvin. Avogadro, we know he's the one that said, oh yeah, 1 mole of gas is equal to 6.02 times 10 to the 23 power. But he also came up with another hypothesis, and he learned that if you have a gas at STP, and down here, STP is defined as 0 degrees Celsius and 1 atmosphere. So when you have a gas under these conditions, we say that 1 mole of that gas, it doesn't matter if it's xenon or methane or oxygen or hydrogen gas, 1 mole of that gas will equal to this many liters if it is at STP. So under standard temperature pressure, we're going to have this volume of gas, and that's what he said. But he also came up with a theory, and remember, a theory is more supported by evidence. A hypothesis is more like an idea, but it's not heavily supported yet by evidence. So what Avogadro's theory just said is that the more moles there are, so the more gas you put into a balloon, the higher the volume. So he came up with this relationship. The next topic, the next thing we did in class was we went over this slide, and I showed you the top half, and I asked you, what do you see? What can we tell from this? And so go ahead and pause it and think about, what do you see here and what do you see happening here? What is the difference? And I told you guys that in chemistry, when you have an arrow and it's longer, it means it's moving faster. It has a higher kinetic energy. It's either moving faster or there's a higher force of attraction. So that's what it means. Go ahead and pause it and think about, what do you see up here? What's happening? Okay, now that you have had time and you paused, the moles remain the same. Okay, so 2 of the same gases, the temperature goes up, and sometimes when we raise the temperature, the volume expands, right? But in this case, the volume is the same. So this is probably a very rigid container. So what we learn from this is that the higher the temperature, you also have a higher kinetic energy. Okay, so that supports the idea that we spoke about in kinetic molecular theory, that kinetic energy is directly proportional to temperature. So go ahead and do the same down here. What difference do you see? Go ahead and pause it. Okay, so from this one, um, you should have noticed that there's 5 times more moles, right? And the more moles there are, um, according to Avogadro's theory, the more moles there are, the higher the volume. But if you notice here, the volume is the same. So Avogadro's um, theory is not really shown in this image. What is shown is that the more moles there are, um, the more collisions there are going to be. Okay, and we could also see that the arrows have the same magnitude, and that's because the temperatures are the same. So because the temperatures are the same, um, the kinetic energy is the same for both. And because the volume of the container is the same, the only thing that changes is just moles. We're adding more moles of gas here. So there is really no law that supports this image. It's just saying that the more moles there are, the more collisions you're going to have with the wall. So the pressure could go up. So we could assume that there's going to be an increase in pressure because there's going to be more collisions. Okay, so the next one, the next slide, I didn't really go over the first 4 bullets. That's something you guys could go over on your own. But I wanted to, you to emphasize this last part. The larger the molar mass, the heavier something is. The heavier the gas is, the slower the particle will be. And that's supported by this formula right here, where if m is smaller, then if you plug in a smaller number for m, you're going to get a smaller kinetic energy. So this idea makes sense with the formula that's up here. So another very important concept is this idea of a real versus a ideal gas. And when we were talking about the ideal gas law, which is PV equals nRT, we made a few assumptions, and the assumptions were that particles don't transfer energy with one another. In reality, they do, but because gases move so fast, we say that they don't transfer that much energy. With the ideal gas law, we assume that they don't experience intermolecular forces or attractions, such as London dispersion forces, and they don't have a defined volume because the gas particles are so tiny. So instead, we say that the gas particles take up the volume of the container. So if for V here, we use the volume of the container instead of measuring the volume of the individual particles. The problem with this ideal gas law is that some gas particles do experience attractions, and they do transfer energy with one another, and that's what a real gas is. However, in order for that to be significant, so in the ideal gas law, even though gas particles do attract a little bit, these numbers that we get for these variables are still legitimate. They're still close enough. But for a real gas, you have to have 2 conditions in order for the data to look different. So the experimental values to look different from that calculated from PV equals nRT. And these 2 variables are low temperature or high pressure. And we talked about this in class. Like, why would, so let me write this down. Why would gases attract, which is violating the ideal gas ideas, let's say. at low temperature and high pressure. And we said that with low temperature, I'm gonna write it here, particles are moving slower. And because they're moving slower, they can therefore attract. And when that happens, we can't really use PV equals nRT anymore, because you have to consider this attraction. You have to include a variable in there that incorporates attraction. And at high pressure, the volume is more defined. And so we cannot assume that the volume of the gas particles is the same as the volume of the container anymore. Because at high pressure, the volume of the gas particles will be more defined. So that's the difference between the two. And I showed you guys in class that they came up with a new formula instead of PV equals nRT, which was used for the ideal gas law, which showed all of these assumptions. The chemist came up with another formula, and again, I said you guys are not responsible for memorizing it. You're not responsible for using it. I don't even know how to use it. I've never tried using it. I'm pretty sure we could figure it out if we had all the units, but it's not necessary. They came up with this, and if you look at this equation carefully, you would notice that it does have PV equals nRT in it. The only difference is this and this. So what they did is they did a little bit of math. I don't know what type of math, but they incorporated two more variables, which is A, which measures how strong gases attract, and B, the volume occupied by the gas. So I'm assuming this is taking into consideration the area, because n squared or v squared is some sort of area. So I'm assuming that's how they found the volume, but honestly I don't really know. But just know that this van der Waals equation was used to incorporate to determine variables like pressure, volume, under a real gas condition. So low temperature, high pressure, and then this idea of attraction and having a defined volume. Now what I want you guys to do is look at this graph and go ahead and look at your notes and see what is this graph telling you, and what would you put in these boxes and why. So read through it very carefully and tell me what you could infer from this graph. Go ahead and pause. Okay, so once you read your notes, you notice that there are different gases, and these gases have different weights. This, for example, has a weight of 4 grams per mole. This one has a weight of 28. This one has a weight of 44, according to a periodic table. And we learned that the heavier something is, the higher the molar mass, the smaller the velocity, right? The smaller the speed. So if CO2 weighs the most, it should be the slowest. And if you move to the left, this is the one that is the slowest. So this should be CO2. He is the lightest, so it should have the fastest speed. So this would be helium, and then this should be N2. What can you infer? So the areas are the same, so we have the same number of moles. This right here, this line represents the helium. I'm sorry, CO2. Most of the CO2 particles have this speed right here. Most of the N2 particles have this speed right here. Most of these He particles, helium particles, have this speed. So that's what we could infer from this graph.